This is Chemistry 473, Transition Metal Chemistry in 2021 Spring Quarter, Exam 1. I'll skip question 1, question 2. We'll name this transition metal complex. First, we need to look at the ligands. There are 3 carbonyl ligands, 3 chloride ligands. In alphabetical order, it's tricarbonyl, trichloride, iron 3. The oxidation number on iron is 3 because each chlorine has a -1 charge. And overall, the complex is neutral, so this is iron 3. And then this is facial isomer versus meridional isomer. So you need to say Fac-tricarbonyl, trichloride, iron 3. Question 3. Name this compound. First, let's look at the ligands. We have 2 chloride ligands. We have 2 triphenylphospheno ligands. And then alphabetical order, well, let's look at this one. Dichloride, bis, triphenylphospheno, all correct. Palladium with a oxidation number of 2. I think this is correct. This oxidation number is wrong. And over here, do not say ditri. Change this di to bis. Over here, this chloride, it's a simple ligand, simple name, so just dichloride, not bis chloride, so do not say bis here. You need to say dichloride, bis triphenylphospheno. Again, when you use bis tris tetrakis in front of a very complex ligand name, usually it's to avoid confusion. So, for example, over here, if you say ditri, I mean, it doesn't sound right. So we change di to bis here in front of a complex ligand name. Another important part of this question is to pay attention to the oxidation number of the transition metal. Again, over here, this triphenylphospheno ligand is neutral. It's going to just give away the lone pair electrons to form the bond. So this is actually neutral, and chloride is considered with -1 charge. So overall, this palladium has to have a positive 2 oxidation number to balance the charge of the complex. Question 4, this is fairly easy. There are 4 chloride ligands, so tetrachloride. But then, since this transition metal complex bears negative charge, so you can't say iron, you have to say ferrite. So it's going to be ferrite. What's the oxidation number? Again, chlorine -1, 4 of them -4. So this iron has to bear a +2 charge. So it's going to be ferrite 2. So tetrachloride, ferrite 2. All right. So these 2 are wrong because of the oxidation number. This one is wrong because it's no longer called iron here. You have to use its Latin name and replace the ending with ate, ferrite. So from ferrum to ferrite over here, this is correct. And also, if you see tetrachloroferrite 2, that's also correct because chloro is the common name of the chloride ligand. Question 5. This question is very similar to the previous question, so you just need to pay attention to the overall charge of the complex. It's negative, so you need to add ate in the end, so coppertate. I think this is only one, coppertate 2, and also tetrabromido coppertate 2. You can say tetrabromo coppertate 2 as well. Bromo is the common name of this bromido ligand. Question 6, oxidation number. Very important. This En1,2-diaminoethylene, this is neutral, so don't worry about this. Each chlorine is -1, so overall you need to have +3 on the cobalt so that 3 minus 2 is +1. So we select 3 here. Question 7. Which of the following ligands cannot be used to form a chelate complex? EDTA, we all know it can form a chelate complex. Diaminoethane, 2 points of attachment. Oxalato, 2 points of attachment. Okay, nitrito. Well, it seems that, this is NO2. It seems that you can, really have 2 oxygen or maybe 1 oxygen to be bonded to a transition metal. But you have to greatly distort the structure of this ligand. So this usually we don't find this ligand to have 2 points of attachment to the same transition metal. So the top 3 options are much better than this option. All right, so question 8. Which of the following ligands may likely form transition metal complexes with a low coordination number? Usually you look for a very large steric effect. How about this? Tricyclohexylphosphine. So you have 3 6-membered rings bonded to this phosphine. So, and also this is actually one of the examples in the textbook by Weller. Question 9. The 2 common structures of 5 coordinate complexes. This is easy, square pyramidal or trigonal bipyramidal. So that's pentagonal. Very, very rare. Very, very rare. I haven't seen any, honestly. So these 2 are really common, and these 2 options are discussed thoroughly in the textbook. Again, square pyramidal and trigonal bipyramidal. Which of the following ligands least likely form transition metal complexes with a coordination number 4? Actually, oxidal, bromidal, and chloridal, they all can be found in a tetrahedral structure of transition metal complex, hydrido. This is a really small ligand, so usually when you have such a small ligand, very likely you'll see this in either a octahedral structure or even higher coordination number. So a coordination number of 4 usually tells you that the ligands tend to repel each other with many lone pair electrons. So oxidal, bromidal, and chloridal, other than the bonding electrons, they all have 2 or 3 lone pair electrons. And also when oxidal is bonded to a transition metal, very often it forms a double bond, for example in permanganate. And double bonds tend to repel each other more strongly than a single bond. So because of this, oxidal, bromidal, and chloridal tend to form a transition metal with a coordination number of 4 instead of 6 or higher. So hydrido is the one least likely forms a complex with a coordination number of 4. It may you may see 6 or even more than 6 when you have a hydrido ligand. Question 11. Which of the following transition metal complexes may have cis and trans isomers? This is pretty easy. First, you need a planar structure, and then cis or trans. Over here, this is a little bit tricky, but this nitrogen and this oxygen may both be bonded to titanium. All right, so it forms a link to titanium. But again, this can form trans versus cis. So these 2 are the correct answer. This one does not have cis or trans because you have 3 chloridal ligands. This one looks right, but it's tetragonal. It's tetragonal. So again, this one cannot have cis or trans. Question 12. Which of the following ligands are ambidentate? You have nitrito, either nitrogen or oxygen. You have thiocyanate over here. What about this one, tricyclohexylphosphine? Only this phosphorus atom can form the point of attachment. What about thiolato? Thiolato has only sulfur that can be bonded to the metal. So it's either thiocyanate, it's SCN, both sulfur and nitrogen can be bonded to the transition metal, and over here it's just either nitrogen or oxygen can be bonded to the transition metal. So over here I should say either sulfur or nitrogen, all right, of this SCN can be bonded to the transition metal. So that's why it's ambidentate, and when it's ambidentate you need to specify whether it's kappa N or kappa S. For this ligand, over here we need to specify kappa N or kappa O. How many isomers are possible for this one? Well, FAC or MER, all right, 2 of them, right? You saw this facial isomer here. This is facial. In the meridional, you need to have the 3 chloridal ligands on the same plane. So if you swap this 2, it's going to be meridional, MER. But usually people just use FAC or MER instead of facial or meridional. in the naming. Question 14. So this is all cis. Intuitively, you would say maybe if it's all cis, I mean cis, well, it should be 1, but it's not correct. It's 2 because of the enantiomers. Because of the enantiomers, when you have this all cis configuration, this structure does not have S1 symmetry or S2 symmetry or S3 or S4. So if a structure lacks S1, S2, S3, S4, those improper rotation axis, then this is optical active with 2 enantiomers. All right, so over here. How many isomers are possible for the planar structure of this? You have fluorido, chlorido, bromido, and iodido. All right, so you can just focus on fluorido and just see which other ligand is on the trans position to fluorido. Well, it can be chlorido, it can be bromido, it can be iodido. Well, 3. All right, what about enantiomers? This structure does not have enantiomers. It's a planar structure. It's a planar structure with a sigma symmetry. And a sigma symmetry is equivalent to the S1 symmetry. S1 means you rotate 360 degrees and followed by a reflection. So it's equivalent to sigma. Again, S1 symmetry is equivalent to sigma. S2 is equivalent to the inversions into I. All right, so again, this structure is planar. So again, I mean, it lacks any improper rotational axis. So there's no enantiomers here. Question 16. The reason for a formation constant to be anomalously large or small, well, it can be the change of coordination number from 6 to 4 or from 4 to 6. It can be the change of the spin state. For example, iron, it can be +2 or +3. So that will cause the change of formation constant and also the change of geometric structure. Question 17, the chelate effect. It's the chelate effect always make the transition metal complex more stable due to the entropic effect. All right, entropic effect over here. So we answered question 17 and 18 at the same time. It's entropic effect because if you just use the same type of atoms, right? If you have like 2 separate ligands, both with a nitrogen atom as the point of attachment versus a single ligand with 2 points of attachment, both are nitrogen atoms as well. So in that case, you form similar bonds. They are both nitrogen to transition metal bond, but over here, entropic effect. That means when you have, for example, 1,2-diaminoethane to form a transition metal complex with a transition metal center, you can imagine that, how about this? You start from a metal bonded to 2 separate ligands, each with a nitrogen atom as the point of attachment. Now you replace these 2 ligands with only 1 ligand, right? With only 1 ligand. So if you look at the reactant site, all right, you have a chelating ligand and a transition metal complex. On the right-hand side, the product side, now you have a 1 transition metal complex and plus 2 ligands. So you go from 2 particles to 3 particles in that reaction. And that involves the increase of the entropy. So again, when we are talking about the transition metal chemistry reactions in, for example, in aqueous solutions or other solutions, my trick is just to count the number of particles on the left-hand side and the number of particles on the right-hand side. All right, if we have more particles on the right-hand side, it's favored entropically. So the chelate effect mostly is the entropic effect. What type of isomerism is possible for this formula? Okay, so this is ionization isomer. All right, so you can have bromide as the counter ion. You can have chloride as the counter ion for the transition metal complex. Okay, what about the other one? So if you have bromide as the counter ion, well, and then this chloride is one of the ligands bonded to the ion center directly. But chloride can be also the counter ion, in the solution outside the transition metal complex. In this case, this bromide is a ligand bonded to this transition metal center directly. Now, question 20. This question is a little tricky, but you just need to focus on the so-called statistical factor. So over here, this L will replace one of the 4 aqua ligands. So 4 possible options. But if you look at the the product side, the right-hand side, if water would like to replace this L, there's only one option. Look, this metal is bonded to 3 aqua ligands and 1 L ligand. Now, if you want to use another aqua ligand to replace this L ligand, there's only one option. Over here, if you look at the forward direction, there are 4 options. So you have a 4-to-1 ratio. All right, 4-to-1 ratio. But now you look at this reaction. Okay, this L again is trying to replace one of the 3 aqua ligands. So 3 options. Now if you look at the reverse direction, water is going to replace L, 2 options. All right, so 3/2. Okay, the statistical factor is 3/2. Over here it's 4/1. 3/2. So 3/2 divided by 4/1. I think it's 3/8. 3/8 is 0.375. This is the closest answer. Question 21. It's actually very similar to question 20. Same analysis, just different numbers. Over here, you're looking at this KF2. The statistical factor is 3/2. Over here, the statistical factor is 2/3. All right, so it's that's why it's different. Okay, so this L can replace one of the 2 aqua ligands here. This water can replace one of the 3 L ligand there. So over here, this is 3/2, this is 2/3. And then you take the ratio between 2/3 and 3/2. Do the math, you get 4/9. 4/9 is 0.44. Okay, it's 0.44. Question 22. Which of the following statements about macrocyclic or macrocyclic effect is true? So you need to form a ring, right? Form a really big ring with multiple points of attachment. So first, it does include this entropic effect, because if you have a large ring to form a complex with a metal with multiple points of attachment, in such a reaction, you're going to see the increase of the number of particles, all right, in the forward direction. So it's entropic effect. And also, it does depend on the size of the ring versus the size of the metal. So if you have a very small ring in a very large metal, it does not fit. All right. So in that case, the macrocyclic effect is small. What if the metal fits the ring perfectly? Well, you have large macrocyclic effect. For example, iron in a porphyrin structure. And now also you have the ligating groups pre-organized on the ring, so that helps the formation of the transition metal complex between a large ring and the metal center. So I'm going to submit the quiz. Oh, I have 3 unanswered questions. So maybe I skipped one. So I need to make sure that I answered all questions. Number 8, number 7, number 6, number 5, number 4, number 3. Well, 5, number 5. I didn't answer number 5. So look at the ligands, tetra, bromido, cobalt, and then don't forget to put ATE in the end. Cobaltate, ATE in the end for a transition metal complex with a overall negative charge. All right, if it's neutral or positively charged, okay, you can just write the name of the metal element. But if it's negatively charged, either you change the ending to ATE or you add ATE in the end, like cobaltate. All right. Okay, I think that's all. Submit the quiz. Okay, let's check. I got 46 out of 52 because I didn't answer question 1. I didn't answer question 2 on Canvas. But again, this is just fact. Tricarbonyl, trichloride, or iron 3 with the oxidation number of 3.